Hello everybody, welcome to another video lesson. We are going to move on to series and sigma notation today. So after this video, we'll be able to use our sigma notation to calculate the sum of series. So let's get into our concepts of what a series is. Well, a series is just the sum of all of the terms of a sequence. So we learned sequences last video, so now we're adding those up to create a series. So we have two kinds. We have a finite series or an infinite series. A finite is just the sum of all terms of a finite sequence, and infinite, of course, is the sum of all terms of an infinite sequence. And we have also what's called a partial sum, and that is denoted as this S sub n, okay, S sub n. So just a few examples here of the difference between sequence and series. We have a finite sequence, 2, 4, 6, 8. The series for that sequence would be 2 plus 4 plus 6 plus 8, and that would have some value. Now an infinite sequence here, 2, 4, 6, 8, dot, dot, dot. So we know if we have these ellipses, then that indicates an infinite sequence. Then the series for that would be 2 plus 4 plus 6 plus 8 plus dot, 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 all the way off into infinity, right? Now our sigma notation now is just another way of denoting these summations. Okay? It's also called summation notation because it indicates the sum of a bunch of terms. And it's denoted with this Greek letter sigma here. So what you might see is something like this. So what you'll see is this here on the left-hand side of our equation. And then what this means is what we have on the right-hand side. So we would read this as the summation from n equals 1 to k of a sub n. The summation from n equals 1 to k, meaning I'm going to start off with my first term as n equals 1, and I'm going to increase n, okay, or increase my term number by 1, going by whole numbers, until I reach k, and then I stop. That's important there. So this is your initial term, and this is your final term where you want to stop. Okay, so we would have a sub 1 plus a sub 2 plus a sub 3 all the way until you reach a sub k, and then you would add all those terms up. So an example here, we would say the summation from n equals 1 to 100 of 4n plus 5. So I would start this off by making n 1. So I'd have 4 times 1 plus 5, and then I would plus 4 times 2 plus 5, and that would be my second term, and then I would go all the way to 100. That's what this sigma notation represents. All right, so those are our two concepts. Let's get into some examples. Finding the nth partial sum. First of all, let's find the sixth partial sum of this recursive formula here on the left. Notice when I have a sub n minus 1, I'm dealing with the recursive formula because I need the previous term in order to find the term of interest. Okay. Now we need the sixth partial sum, which means I'm looking for s sub 6, right? Or I need 6 terms really that I'm going to add up. And they give us the first one, that's going to be 8. So then my a sub 2 would be 1/2 times a sub 2 minus 1. Well, that's just a sub 1, which it was given to us as 8, so it's going to be 4 for a sub 2. And then we keep going, so 0.5 a sub 3 minus 1, so that's going to be a sub 2. So that would be 0.5 times 4, or 2. Now I would take that 2 and plug that in, and I would just keep going for 4, 5, and 6. Okay, so for a sub 4, that would be 0.5 times a sub 3, or 1. And then we have values for 5 and 6 as well. So s sub 6 is going to be a sub 1 plus 2 plus a sub 3 plus a sub 4 plus a sub 5 plus a sub 6. So we just add all these terms up that we just found, and we get s sub 6 value of 15.75. Now you guys pause the video and see if you can find the seventh partial sum of this sequence right here. Alrighty, hopefully you realize that as the denominator got larger, as my n value got larger, that meant my denominator got larger, and that meant that my term actually got smaller, right? And we added a decimal point each time. So the s sub 7, the seventh partial sum, was 0.33333. So 7 3s there. All right, example 2, sigma notation. Again, we have the same prompt. We're just finding the sum here. Okay, remember, sigma notation also referred to as summation notation. So understand both of those depending on what verbiage you are dealing with in the context of any problem. All right, so first thing we're going to do here, we're going to input 1 for n, and this is going to be my first term. Okay, n equals 1, that's my first term. Now, n we refer to as a dummy variable, so that is going to increase by 1 every single time my term increases. So next term I have, I'm going to add 2 squared minus 1 over 2. Again, my n is just going up by 1 each time. This is my second term here. Now, my third term, I would have n equals 3. Fourth term, n equals 4. And fifth term, I would plug in 5 for n. And then we can just go ahead and start simplifying this. So we have, in decimal form here, 0 plus 1.5 plus 4 plus 7.5 plus 12, and that's going to be 25. All right, last example here, we have sigma notation, but we have, notice here, my k value, or my last value, my final value, is actually infinity. So let's see what that looks like. Okay, I would have 6 over 10 to the first power. Okay, this is my first term. And then I have plus 6 over 10 squared. So that's my second term, third term, fourth term, fifth term, and so on. This is going to go on forever, right? Because my final term is infinity. So it just doesn't stop. It just keeps going. Now, what does this look like when we start to simplify? So I've got 6 over 10 plus 6 over 100. And hopefully you can realize that if we were to put this in decimal form, again, similar to our last problem, we're just adding a decimal every single time, right? So what does this look like when I start to add all these up? Well, I'm just adding a 6 at the end every single time, which looks like 6 repeating, which we actually have an exact value for, right? That's going to be 2 over 3. All right, guys, so that was it. Quick video there. Good luck with your practice.